Integration by parts. Every differentiation rule has a corresponding integration rule. For example, we saw that the substitution rule for integration corresponded to the chain rule for differentiation. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts. So let's revisit the product rule. What does it state? Well, it states the following. Given two functions, u and v, so given u, which is a function of x, and v, which is a function of x, that are differentiable, remember, differentiable means their derivative exists throughout their domain, let's say, be differentiable functions. And let's suppose further that their derivatives, so u prime and v prime, are continuous functions. So u prime and v prime are continuous. Okay, so we can integrate them. All right. Then the product rule says that if you differentiate with respect to x the product u times v, right, this product of two functions, each of which is a function of x, you get the derivative of the first, let's say, times v times the second plus the derivative of the second times the first. Okay, and this is simply by the chain rule, correct? Sorry, by the product rule, by the product rule. Very good. Okay, now what can you say then? This entails that this product uv is a primitive or an antiderivative of this entity here, or this function. So a primitive function of u prime v plus uv prime dx. So this primitive is equal to uv. uv is an antiderivative of this guy, right? Okay. Now, since the integral of a sum is the sum of the integrals, this is the same thing as saying that the primitive of u prime v dx plus the primitive of uv prime dx is equal to u times v. Correct? Here, because the primitive of a sum is the sum of the primitives. Very good. And this means then what I'm gonna do is I'm gonna take this entity and move it to the other side, right? So something plus something else is a third thing. This means that the first thing is equal to the third thing minus the second, correct? So we get primitive of u prime v dx is equal to u times v minus the primitive of uv prime dx. And here I just move this guy again to the right side. So we get this formula. So we get this formula right here. And this formula is called the formula for integration by parts. Okay, so this is called formula for integration by parts. Let's keep it capital here, so let's take the I to be capital. And let's create an acronym for this, IBP, for integration by parts. Okay, so from there on, if I say IBP, I mean integration by parts. So let's take a look at the formula itself. What does it say? Well, the first thing I realize is if you try to integrate this function u prime v, if you try to find this primitive here, where the operator d over dx, the differentiation operator, you see it, it's right there, the notation is prime here, it's acting on u on the left side, whereas on the right side, it's acting on the v, correct? So what I'm saying is, this entity here, let me just highlight it for you. So this thing here, I'm talking about the derivative of u, right, within the integrand. And here I'm talking about the primitive of u times v prime. So the prime has changed from acting on u to acting on v. Okay? So integration by parts, it's an effort to actually switch the operator that's acting on the differentiation operator that's acting on one of the functions to the other. Okay, so it's an effort to actually make this change from acting here to acting on the other one, v. And the objective in using integration by parts is to obtain a simpler integral, right? Is to obtain a simpler integral. So you do the switch, you pay a price. This is the price to pay, and also changing the sign of the integral. But the objective is to obtain a simpler integral than the one that you start with. So the idea is, whatever integral you have, if you observe that switching the differentiation operator from one factor to the other, u being one factor and v being the other, so from switching it to the other, right, allows you to move to a simpler integral, or at least not more complicated than the one that you have, then you can do so via this formula and by paying this price right there. Okay, so you don't get to move the operator freely. You have to pay a price, and that's the price to pay. Okay, so that's the essence of integration by parts. Let's now apply the formula and go to the book to page 529, and let's do let's say number 14. So we want to integrate, using integration by parts, we want to integrate x cosine 4x dx. And let's ignore the hint. Let's ignore this part here. Okay, so that's on page 529, number 14. And we would like to integrate the function x times cosine of 4x dx. Okay, so based on earlier knowledge, we cannot integrate this function. If you go for u substitution, the derivative of 4x is 4, and there's an x here, so u substitution doesn't apply here. So really we cannot do anything based on earlier information or earlier knowledge. So now let's observe the following. If this guy is not there, we can integrate using the u substitution that we just discussed. If it's not there, right? If this doesn't exist over here. And what we can do based on this formula, the integration by parts formula, we can make it disappear in some sense by taking its derivative, right? Because if you differentiate this x with respect to x, you get a 1. And if you get a 1, then you are integrating a trig function. Okay? So I would like to move that operator to the other one, to the other factor. So the operator, in this case, is gonna be acting on this. That's the one that's gonna play the role of u prime, and the x is gonna play the role of v. Correct? Because when you transition to the right side, the v is gonna now be differentiated, so the x is gonna be differentiated, and hence no more, in some sense, no more x. So you get a 1, and then you integrate the trig function using a regular u substitution. Okay? So that's the idea here. Let's try it. So let's set, as we said, the u prime to be cosine of 4x. So let's set u prime to be cosine of 4x, and the v to be the x. Okay, so and the v to be the x. As such, what do you obtain? What is it? What is an antiderivative of cosine of 4x? What's a primitive of cosine of 4x? Well, it's 1 over 4 sine of 4x plus some constant, right? I agree with that. So because if you differentiate this, if you differentiate that, you get exactly u prime. Okay, so this is what you have. And if v is x, what do you obtain for v prime? By prime I mean derivative with respect to x, you get a 1. Correct? Okay, so now I know what u and v prime and v are, so I'm gonna put them here. These are the ingredients I need to move to the right side, right? Okay, so what I'm gonna do is I'm gonna write equality, and all this package that I just came up with is gonna be needed in transitioning here by making use of IBP, integration by parts. Okay, so what do we get? We get uv, right? The integral of u prime v dx, this is u prime, this is v now, is equal to uv, and what's u? U is this entity, 1 over 4 sine 4x plus c, that's the u, times the v, and who's the v? It's the x, correct? Minus the primitive of uv prime of u, this is u, so 1/4 sine 4x plus c, that's the u, times v prime, the v prime happens to be 1, correct? Dx. Okay, so we're not integrating this anymore. Look here, for uv, we're not integrating this entity, it's just part of the answer, right? It's part of the primitive. But that's the integral you have, and take a look at this integral. This is way simpler than the one we started with, right? We can use u substitution here and finish it, correct? So let's keep going. So this entity is equal to 1/4 x sine 4x plus c times x, the constant c times x, minus, all this guy is minus 1/4 primitive of sine 4x dx, right, dx, plus the primitive of c dx, with a minus it becomes a minus here, of c dx, correct? Okay, and as I promised you, this is now easy using u substitution. It's very much like we did to go back from u prime to u. And what is that? This is negative, right? 1/4 cosine of 4x plus some other constant, let's call it k. Okay, and how about this guy? How about this guy? Well, this is simply cx plus a new constant. How about a for a constant? So c, a, and k are all constants of integration, correct? Okay, so now let's write down where we are. We finished the integration because we found the answer for this and we found the answer of this. So we got 1 over 4 x sine 4x plus cx minus, well, minus the minus is plus 1 over 4 times 1 over 4 is 1 over 16 cosine of 4x, cosine of 4x. Now the minus times the plus is going to be negative 1/4 k, so k over 4, right? K times 1/4, minus the cx minus a. Okay, so we get this one. And then what do we obtain? Well, we observe that the cx and the cx cancel, They have opposite signs. And then we get this equals 1 over 4 x sine 4x plus 1 over 16 cosine of 4x, right? Minus k over 4 minus a, where k and a, don't forget, k and a are constants of integration. They are arbitrary constants, right? Arbitrary real numbers. Okay, so we get this. Let's zoom out and let's put things together. This entity now, this primitive that we had earlier, I'll highlight it, this one, is now equal to all this guy, correct? Where k and a are arbitrary constants. Let me write that down for you. Where k and a are arbitrary real numbers. Okay? Now, here's a question for you. If k and a are arbitrary real numbers, what can you say about negative k over 4 minus a? Well, if k and a can be anything, then this guy here can also be anything, correct? Because a and k can be anything, can be any real numbers. If a and k can be any real number, this entity here can be any real number. Let's give it a name. How about the name, what can be a name for this? How about the name t, okay? T for this constant. Make sense? So what I can say then is, this becomes equal to 1 over 4 x sine 4x plus 1 over 16 cosine of 4x plus a constant t, where t is arbitrary real number. This means t is an element of R, right? R being the set of all real numbers, and this means element. So t is an element in R, arbitrarily chosen. Arbitrarily chosen. Okay. Because t is the opposite of k over 4 plus a. This entity, since each ingredient is arbitrary in R, the whole thing is arbitrary in R. So t becomes an arbitrary real number. Okay? Alright, so this guy then is the primitive of x cosine 4x. You can check, you can differentiate this whole thing, and you must get this integrand. Okay? Alright. What if we did, so we finished this problem. What if we did the other way? What if we did, instead of choosing this to be the v, right? Instead of choosing the x to be the v and the cosine 4x to be the u prime, what if we chose the other way? What if we chose v prime to be x and u to be cosine 4x? We could have then, if v prime is x, then v would have been x squared over 2 plus a constant, correct? And we could have, instead of moving on to an integral which is that simple, we would have gotten another integral which has to do with x squared over 2 times something like this here plus a constant. So this integral, what I'm saying is, this integral here would have been more complicated than the one that you started with. And as such, you're not simplifying your problem, you're actually making it, you're not retaining it actually at the same level, you're making it more complicated. So a careful choice of the ingredients u prime and v should allow you to pass to an integral which is at worst not more complicated than the one you start with. Okay? Ideally, this should be simpler than the one that you start with. So I encourage you actually to take the time to write the details for the other choices, u being u prime being x and v being cosine of 4x. Okay, so probably I reversed them earlier, but this is what I meant. So what I'm saying is, if we suppose u prime to be x and v to be cosine of 4x, u would have been x squared over 2 plus a constant, and v prime would have been negative 1/4 cosine sine of 4x plus a constant, correct? So the idea is this integral is going to be more complicated than you start with. You're going to have x squared in concert with a trig function. Okay? So, and this is not the idea of integration by parts. Integration by parts should allow you to pass from an integral to another. At worst, it should be not more complicated than the one that you start with. Okay? All right. So please take the time to do it and see why this choice is better. Another thing I wanted to highlight is, what if here we took the constant c, since c can be anything, right? Since c can be anything, what if we took it to be 0? Is there any change that happens in the, later on in the discussion? Let's follow where c sits. If we take c to be 0, this is gone, right? This is gone, and that's gone. And what we get, we don't get this term. We don't get this term because we're taking c to be 0, right? And let's also all right, you know what, let's keep going. So let's take this c to be 0, so all these x's are gonna disappear, and hence this is gonna disappear and this is gonna disappear, right? And this is gonna disappear because this is coming from this guy. Okay, all right. I mean, you may say, oh, what if this is 0, then this can be a pure constant a. Sure, but this a with the k, or the negative 1/4 k, are gonna make up a new constant, correct? So so this can also be taken 0, and as such we only end up with negative k over 4, and that negative k over 4, if k is arbitrarily chosen in R, then negative k over 4 is going to also be arbitrarily chosen in R. So we get to this point at the end of the day by taking c to be 0. Correct? So instead of carrying this c from the get-go here, instead of carrying it from one stage to the next and getting to the same answer, how about we actually take the simplest c possible, which is 0, from the get-go, so we don't have to actually write more stuff to get to the same answer. And this is not just for this particular example. You can make the case for the abstract context. I mean, just imagine you have here a constant, right? So just imagine for the abstract context, when you integrate u prime, you get a c, you get a constant. Along the way, that c is gonna sit here, and it's gonna also sit here, right? So it's gonna sit right there, and it's gonna sit right there. And because it's a multiplicative constant here, it's gonna go outside, so it can sit outside. And then you're back to integrating v prime. And when you integrate v prime, you're gonna get something that has to do with v. And then that constant times v minus the same constant times v is gonna also, they're gonna also disappear like they disappeared here in the abstract context. And you're gonna carry a new constant which can be combined with the other one that's gonna come from this term, right? The term that's gonna exist also here. And you can, at the end of the day, since all the constants are arbitrarily chosen, you can combine them together and make up a new arbitrary constant also coming from the set R. Okay? So to summarize, we observe that choosing a constant doesn't make a real difference at the end of the day. And we talked about it. We can actually make the case by writing it, but I'm not gonna do it feel free to do it, obviously. The constant the constant when you do the integration by part can be taken to be 0 to simplify matters, because at the end of the day you can combine arbitrary constants to come up with a new arbitrary constant. Okay, so long story short, when you integrate by parts and you set your u prime, you want to go to u, don't add that typical constant c. Choose that constant to be 0, because as we just discussed, it's not gonna make any difference at the end of the day. All these supposed constant that you're gonna pick up along the way are gonna be embedded in a new arbitrary constant. Since those were arbitrary, this final one is gonna also be arbitrary, and the answer is gonna be the same no matter what. Okay. All right. So back to the book. Let's do a problem. Let's say 20. So we would like to integrate x5 ln 3x dx. Okay. So that's on the same page, and this is number 20. We want to integrate x to the power 5 ln of 3x dx. Okay. All right. So this is a product. Again, if you try here to do any other approach other than integration by parts, you're not gonna be successful. U substitution here doesn't work, because if you set this to be u, the derivative is 3, so you're not gonna pick up the x to the power 5. And you can actually convince yourself that you don't have the tool besides the integration by parts to actually integrate this function here. So so I need to apply the integration by parts. The question is, which one should I use as u prime, which one should I use as v, so that I transition to a new integral which is at worst not more complicated than this one, right? So what I'm gonna say is I'm gonna set u prime to be x to the power 5 and v to be ln of 3x. If you try the other way, if you try v to be x to the power 5 and u prime to be ln of 3x, then you would have to integrate to go to u, right? So to go to u, you would have to integrate ln of 3x, which is not an easy integral to do. As a matter of fact, if you want to integrate ln of 3x, you have to go through the integration by parts formula. Okay. All right. So I'm left with this choice. Let's try this choice if it works. So if u prime is x to the power 5, what is u? Well, u is I'm integrating, so I'm gonna get 1 over 6 x to the power 6 plus a constant. But as discussed before, let's take the simplest constant possible, which is 0. Because the final answer doesn't change by the choice of that constant c. Okay, and then if this is v, what is v prime? What's the derivative of v? What's the derivative of ln of a function which is a function of x? Well, it's the derivative of the function, so it's the derivative of this guy, which is 3, divided by the derivative, divided by this argument, which is 3x. Correct? So this is actually 1 over x. Okay? So I found all the ingredients that are needed actually to transition from the left side of the integration by parts formula to the right side. So I'm going to get uv minus the primitive of uv prime dx. So I'm going to get, so I'm using this package to apply IBP, and I obtain uv, so u times v, so 1 over 6 x to power 6 times ln of 3x minus, that's integration by parts if you remember above, minus the primitive of uv prime, right, of u times v prime. So it's going to be 1 over 6x6 times 1 over x. So let's make some room for the multiplicative constant to sit outside. 1 over 6. x6 times 1 over x is x5, right? Is x5 dx. So we get this, which is way simpler, right, than this one. Okay. Alright, and then this is going to be equal to this guy. This was already, I mean, you don't have to integrate this anymore. We don't have integral associated to this. It's 1 over 6 x to power 6 ln of 3x minus 1 over 6 times the primitive of x to power 5 dx. What's the primitive of x to power 5? It's very much like this here. So it's 1 over 6 x to power 6 plus a new constant or a constant of integration. Correct? So if you added a constant here, you're going to combine them, and at the end of the day, you're going to have this new constant. And this is arbitrary, right? So where c is an arbitrary constant and r. Okay. Sure, this is 1 over 36 and so on. Let's actually write the final answer. So we get 1 over 6 x to power 6 ln 3x minus x to power 6 over 36 plus c, where c is an arbitrary constant. Okay. Alright, since I was talking about the other set of choices for u prime and v, and I told you if you choose u prime to be ln of 3x, to transition from u prime then to u, you're gonna also need integration by parts. Let me illustrate this point. Let's take this example. So let's integrate let's just take ln of x dx. Okay, if you take 3x, is not a big change. So let's integrate this one. Here we don't have much choice for u prime and v. What I'm gonna do is I'm gonna take u prime to be 1 and v to be ln of x. Okay, as such, remember the idea is to transition by integration by part. You want to transition to an integral which is not more complicated than the one that you already have. If u prime is 1, then u is going to be x plus a constant, but again I'm going to take the constant to be the simplest possible. And if v is ln x, v prime is going to be 1 over x, correct? Okay, so I'm using integration by parts with these choices. So integration by parts, and I obtain what? So if you go back to the formula, it's u times v prime, it's u times v, so x ln x, minus the primitive of uv prime dx, right? And u is x, and v prime is 1 over x dx. Okay, and this integrand here is simply 1, right? Because x divided by x is 1, and we obtain that this is don't worry, here x cannot be 0, right? You may think, oh, x can be 0 and so on, but it cannot be 0 by design because ln doesn't operate on 0. Okay, so don't worry about this. This is meaningful here. And you get x ln x minus the primitive of 1 dx, which is x ln x minus x plus some arbitrary constant. So where c is an arbitrary constant and r. correct? So what's the primitive then of ln x? Is x ln x minus x plus c. You can factor out an x here and read it as x times ln x minus 1 plus a constant of integration. Let's go back to the book and let me just do number 17 here. So we want to integrate x cubed times ex. So that's number 17. We want to integrate x cubed times ex dx. So observe that x cubed becomes simpler when we differentiate it, whereas ex remains unchanged when you differentiate it or integrate it. Okay, so I'm gonna choose x cubed to be the v. So I'm gonna choose the v to be x cubed and the u prime to be ex. Okay, as such, u is ex, or can be chosen to be ex, and v is, or v prime is 3x squared. Okay, so let's use integration by parts here with this package, and we obtain u times v, so u times v, so x cubed times ex, minus the primitive of uv prime, right? This is what the formula was. Let me take you back there. This is what the formula was, right? I'm talking about this. uv minus the primitive of uv prime dx. Okay, so minus the primitive of uv prime dx. So ex times 3x squared. So 3 is a pure constant, multiplicative constant. You can push it all the way outside. And then we get x squared times ex dx. Okay, so the problem now is down to this. It looks like we still have an integral of this form to integrate, but realize that the power here has decreased by 1. Okay, which means if we do integration by parts one more time, this power here is going to decrease 1 more, so to get x ex, and then a third time is going to reduce this x to power, this new one, it's going to be x to power 1 to x to power 0, which means 1. And then you're going to only have ex at the end of the day. So just simple inspection allows us to realize that I'm going to do integration by parts 3 times. Okay, the first time we got to x squared, we reduced by 1. Another time is going to allow us to decrease it 1 more time, so to x. And then the last time is going to allow us to just bring that constant 1 ex, which is easy to integrate. Okay, so it's 3 times integration by parts just by simple observation here. Let's keep going then. How about we call this entity here j. Okay, how about j1 for, after integrating the first time by parts. Now let's look at j1. j1 is equal to primitive of x squared times ex dx. Integration by parts again. Is gonna tell us to obtain the following. Well, let's first understand who u prime and who v are. Well, I'm gonna still have the same choice to decrease it by 1, right? To decrease this power by 1. So I'm gonna have u prime to remain ex and v to be x squared. Then u is ex plus a constant, but we're not gonna carry constant. We're gonna just have 0 because again the final answer doesn't change based on the choice of that constant. And v prime is 2x. Okay, so that would be the new package for integration by parts, and we obtain uv, so x squared ex, right, this times this, minus primitive of uv prime. right? The formula says minus the primitive of uv prime, which means minus 2x ex. And since 2 is a multiplicative constant, I can put it outside. X ex. Sorry, x. Yeah, x ex, right? This dx. Very good. Okay, so now as promised, now this power 2 has decreased by 1. Now it's 1. Now last time is gonna allow us to force this to disappear, right? We're gonna have a x to power 0, which is 1. So one more time, let's choose a new color. So let's call this guy j sub 2, and let's do j2. j2 then is equal to, or which is defined to be x ex dx. If you integrate by part, again, so technically this color here should be blue, right? Same this. Okay, anyway, so integration by parts, I'm gonna set same thing, u prime to be ex, which force u to be ex, and v to be x, which force v prime to be 1. Correct? This would be my package this time for integrating by parts, and I obtain u times v, which is x ex minus the primitive of u v prime, so 1 times ex, so ex dx. And now, well, first of all, as we discussed before, the power here of x is 0, it's down to 0, which means 1, so we're done. And then this is an easy thing, right? This is an easy integral. What is this integral? This is ex plus an arbitrary constant, correct? Plus an arbitrary constant. Let's keep the constant. Let's add the constant at the end, because you know what? Let me just put the k here and show you why I can just add it at the end of the day. Okay. Let's keep it for now. So keep in mind k is an arbitrary constant, right? So where k is an arbitrary real number. Okay. All right. So we found j2, and hence we found j1. And if you find j1, then you found the desired integral, right? Let's give it a name. How about j for that integral? Okay, so we're gonna collect information now. Then j is equal to x cubed ex minus 3j1 minus 3 times the j1, and the j1 happened to be x squared ex minus 2j2, right? And j2 is this, so minus 2j2, and j2 happened to be x ex minus ex plus k. That's what j2 is. Okay, so one more time, j is equal to x cubed ex minus 3 times j1, and j1 is x squared ex minus 2 times j2, minus 2 times, and this is j2, right? X ex minus ex, technically it should be minus k. All right, let's keep it minus k. Okay, and we get this, right? And k is an arbitrary constant in R. Very good. So now that's the same thing as saying x cubed ex minus 3x squared ex plus 3 times 2 is 6 x ex plus, with this minus it becomes a minus, 6 ex, right? And minus 6k. 3 times 2 times k is 6k, minus times minus times minus is minus. So you get 6k. And that's what I was talking about. This whole thing now can be thought of as a new constant. Since k is an arbitrary number in R, this thing, minus 6k, can also be an arbitrary number in R. So how about calling it C? Okay. So we get then x cubed EX minus 3x squared EX plus 6x EX minus 6EX plus C, where C is an arbitrary constant in R. So where C is an arbitrary constant in R. Okay. You can factor EX here among all these 4 terms here and just have EX in factor of x cubed minus 3x squared plus 6x minus 6. Correct? And observe that each term here, each function that's multiplied by EX each time is the derivative of the preceding one, and that's because of the process, right? And that's because of the process, because we did integration by part 3 times. So x cubed we differentiated 1 time, another time, and a third time. Alright, so people have realized whenever you are doing repeated application of integration by parts, there's something called tabular method that you can employ that can organize in a compact way the process. So let me just illustrate that. But I mean, I'm still talking about the same example, okay? Because we did integration by part 3 times, and as I mentioned, people have realized that they can write it in a compact way. This whole process can be written in a compact way. So let's rewrite G. So here using, so this is an alternative approach, right? Alternative approach. It's not an alternative approach. It's an alternative way of writing the process. Okay. All right. I'm gonna put quotation here. So we had J equals primitive of x cubed EX. This is the tabular method. So the tabular method. So use a table, right? We're gonna be using a table, and the observation is as follows. So you create a table between those two functions, namely x cubed and EX. Okay, and we differentiated this guy along the way above, right? So this side we're gonna differentiate this function all the way to reach its to annihilate it. Because if you differentiate x cubed, eventually you're gonna reach 0, right? So differentiated 1 time, you get 3x squared. Differentiated another time, you get 6x. Differentiated a third time, you get 6. And differentiated the last time, you get that 0 that I was talking about. Correct? So on this side, you differentiate. On this side, okay, so you differentiate here, and over here you're gonna integrate. So over here you're gonna integrate all the way to that same stage. And what do we obtain? Well, if we integrate EX, we're gonna get EX each time, right? So integrate EX, we're getting EX each time. So we're integrating, not differentiating, because also if you differentiate, you get EX. But that's not what we're doing. We're doing integration as we did above, right? What were we doing with the EX? We were integrating it each time, right? So from U prime to U. So we're integrating, and so on. Okay, and then finally, how would you read the table? Well, again, this is an observation, okay? This is an observation. So people have realized that this tabular method is a compact way to represent the work above. The reason behind this tabular method is that discussion above. Okay, so don't confuse, don't say, oh, how did or why am I doing this way. It's an observation that people made the connection between a compact representation of repeated application of integration by parts. So how does that go once we differentiated this left column and integrated this right column? So you multiply these guys, you multiply diagonal expressions, so x cubed times ex, and the sign is gonna be important. So the sign here is gonna be a plus. This times this diagonal product is gonna carry the sign minus. The product of these two is gonna carry the sign plus. The sign is gonna alternate, and then the last one is gonna carry the sign minus, right? Plus minus plus minus. You start with a plus all the time, and then you carry that sign. And these signs are coming from the formula, the IBP formula. I'm talking about this sign here. Okay, so that's the sign that's gonna show up. Okay. All right. So J then is J then is equal to x cubed ex with a plus sign. So plus x cubed ex. Okay, so that's this term. That's this term, correct? Which was coming from whenever we did the long process. It was this guy, which has the sign plus coming from this guy, the sign plus, and then we're gonna have the minus, correct? And then you're gonna have the minus this times this, so 3x squared ex, and then with the plus sign 6x ex, 6x ex, and the minus 6 ex, so this takes care of this, plus that constant of integration that you're gonna pick up at the end. Okay, and now if you compare the two answers, what's written here in pink and what's written in purple, they're the same, right? X cubed ex minus 3x squared ex plus 6x ex minus 6 ex plus the constant of integration c. Okay, so this tabular method is is useful. Probably don't see it too much at the level of when you have 3x cubed. What if we have x to power 10? The process before, sure, it's gonna yield the same answer, but this is gonna be long. You're gonna have to integrate by parts 10 times. It's gonna be multiple pages, as opposed to just a table of a certain number of rows, right? So this is useful, and this is applicable whenever you are integrating. I forgot to write dx here, my bad. So whenever you are integrating a polynomial, this is a polynomial. Doesn't have to be a monomial. It can be a polynomial against either an exponential function or sine or cosine. Okay, so this can be also replaced by sine and cosine, but the same game remains true, because if you differentiate any polynomial, eventually it's gonna reach 0, and you just integrate that other function, whether it's exponential, sine or cosine. Okay, and then you play the same game to get to the final thing, which is the primitive of that given function, which is the product of these two factors. Okay, so that's useful, tabular method, but if you don't want to use it all the time, you have to do a repeated application of integration by parts. Since we're talking about tricks, let me tell you about another trick that's called, so there's like an acronym, it's called ILATE. Again, this is discovered by people that realized that this thing would be useful to do integration by parts. And let me first tell you what each letter means. I means inverse functions. So inverse trig functions, let's say inverse trig functions. L for logs, for logarithms. A for algebraic expressions, so algebraic. T for trig, so trig functions, and E for exponential. Okay, so I again, it's for inverse trig functions. L for log, A algebraic, T trig functions, and E exponential. Why this is useful? Well, whenever you are integrating, you a product of two functions, you characterize the class of each one of them. Let's say you are integrating an algebraic expression, like in the case above, it was x squared, right? And ex dx. So this would be algebraic, so it's of class A, and this would be of class E, which is exponential. And what people have realized is whichever comes first from the left, which in this case annihilate, in this case A comes before the E, right, from the left, it takes the role of V. So it takes the role of V. So as you saw in the process, oh, it was x cubed, but anyway, you got the idea. So that's gonna be the role of V. So V is gonna be the algebraic in this case. Okay. So in this case, this is x cubed, and A is gonna be before E in annihilate. So as such, that's gonna be the V guy, and the other is gonna be the U prime in the integration by parts formula. Okay. So this is just what people realized. I mean, whichever class occurs first, they realized that there is a common theme that, you know, the one that comes first actually takes the role of V. Okay. You can see it in previous. For example, here in this example, for ln x, we had a 1 and we had the ln x. So the 1 is of class A, algebraic, right? And the ln is of class L, and in annihilate, L comes before the A. So that's the guy that's gonna play the role of V. Okay, as we saw here. Okay. Let's scroll up just to go to the previous one. Similarly here, this is an algebraic expression, and this is a logarithmic expression, and in annihilate L comes first, so that's gonna be the guy who's gonna play the role of V. Okay, in the IBP. And in the first example, we had x, which is algebraic, and we had cosine, which is trig. And in annihilate, A comes first, so that's gonna play the role of V, and that's gonna play the role of U prime. Okay. All right. So it's just an observation, but it's useful. However, with that said, if you have if these two guys happen to be one I, one L, or one T and one E, okay, it doesn't matter which one takes the role of V. So here they're the same. So if both of them sit in this loop or both of them sit in this loop, so meaning in this loop one is I, one is L, so inverse trig and log, it doesn't matter which one you take to be V. And if one is trig and one is exponential, again, it doesn't matter which one you take to be V. Let me illustrate this point via an example. So let's take the following example. So let me just change this. let's take the following example. Integrate I, which is the name of the integral, let's say, to be defined as follows: ex sine x dx. Okay, so here this guy is in class E and this guy is in class T, so and they're in this loop, right? It doesn't matter, as I said, it doesn't matter why, or it doesn't matter which one is gonna be V. And let me show it to you. So we're gonna use integration by parts. Use integration by parts with, again, it doesn't matter which one you take V and which one you take U. So, sorry, which one you take V and which one you take U prime. So let's say U prime is EX and V is sine X. Okay? So as such, U becomes EX and V prime is the derivative of sine, which is cosine X. Correct? Alright, and then I becomes by integration by parts, we get U times V, so EX sine X minus the primitive of UV prime dx, so EX cosine X dx. Correct? Okay. So, and now we're gonna realize that I, which is this guy, we transition to a new one, to a new integral, which is not less complicated than this one, right? We're still having this class exponential against trig. However, it's not more complicated, right? It's at least not more complicated. So it's at the same level of complication. But if you take a moment to think about it again, what if we do integration by parts one more time? If you do integration by parts one more time, the cosine is gonna become a sine, right? Because, I mean, if you integrate sine, you go to cosine, and if you differentiate sine, you go to cosine. If you differentiate cosine, you go back to sine, up to a change of sign, obviously. But the idea is we're gonna go back to sine if we do integration by parts. Okay? So let's keep riding our luck here and see where this is gonna lead us. So let's use integration by parts again with U prime, same choice, U prime to be EX and V to be sine X. As such, U is gonna be EX and V prime is gonna be, sorry, I meant here to write cosine. I was copying the same thing. Here I meant cosine of X, right? Because that's gonna be the V. And as such, V prime is gonna be negative sine X, right? Okay, so one more time. I'm using IBP for this entity here, for this integral. So U prime is gonna be EX. I'm gonna preserve the choice of U prime, which was the exponential function. I'll tell you why later. And I'm gonna preserve the choice of V to be the trig function, and the trig function happens to be cosine here. As such, V prime becomes minus sine and U becomes EX. Therefore, if you call this, how about we call this guy W? Okay, so therefore W is equal to, by IBP, it's gonna be equal to what? UV, so EX cosine X, minus the primitive of UV prime, so minus the primitive of EX times negative sine X. Negative times the negative is plus EX sine X. Correct? Sine X dx. Dx, right? Okay. And this is I, right? This is the I that we had above. This is I. Okay, so that guy is I. So W is simply EX cosine X plus this guy is I. So putting things together, we can say that I is equal to, I'm talking about this equation, I is equal to EX sine X minus W, right? Minus W. And how much is W? Is this package. EX cosine X plus I. One more time. If I was EX sine X minus W, and W happens to be EX cosine X plus I, so I have EI equals EX sine X minus the package W. Okay? Alright. And this means that I is equal to EX sine X minus EX cosine X minus I. Right? Okay. Alright. And then let's solve for I, because that's the desired thing. We want it to find what I is, correct? So let's solve for I. This means that, how do you solve for I here? You add I to both sides, right? You add I to both sides. If you add I here, you get 2I. And if you add I here, you lose this I. So you get EX sine X minus EX cosine X. Do you agree with me? So you get this. What's the desired thing again? It's the I. So if twice I is this much, this means that I is half of that, right? So this means that I is simply half of EX sine X minus EX cosine X. Okay? So I forgot to add the constant of integration. Let's add it at the end. So let's just add it at the end, because I itself is an integral, right? It's an indefinite integral. So technically I should have added a constant probably here, but it's okay. Let's just add it at the end. So we get, so therefore I is this plus a constant of integration. Okay. Here's a question for you. What if here in the process, remember we did integration by parts twice. What if in the process one time we took u prime to be ex and v to be sine x, and the other time we swap them? What if I take here, for example, I take u prime to be cosine x and v to be ex? Can you think what could have happened if we swap? If we didn't preserve the choice of the v, so here the v was trig and here the v is trig, right? What if one time I took the v to be trig function and the other time to take it to be ex? What could have happened? So take a moment to actually see what could have taken place. I'm gonna just say you should observe that we undo step one, so we kind of go back to the original one. So we technically we could have not done anything. Okay, so we kind of if you do it as such, you're gonna undo what you did in step one in some sense. Okay, take a moment to think about it and write the details out. Okay, so this example illustrates what I just said here. When you have when you integrate trig against exponential, the choice doesn't matter. And by this I mean you're gonna go in circle, and when you go in circle, you're gonna find again that guy that you start with, but it becomes solving an equation, and you got you can actually get what you wanted. Okay. Another thing, how about you try on your own? You take u prime to be the sine here and the v to be exponential, but you have to also preserve it over in the second stage. You also take u prime to be cosine and you take the v to be exponential. Okay, so as long as you are preserving the choices, you're gonna go in a circle, but that's gonna be helpful because at the end of the day, it's gonna come out as solving an equation for that desired integral. Okay, so try what I just discussed. I discussed two things. One thing is, if you don't preserve the choice, if you take one time v to be trig and the other time to be exponential, see what happens. And the other time is, what if you swap, in both cases, you swap the choices of v and u prime. So take the v to be exponential and the u prime to be trig in both, and you're gonna get to something very similar. Okay, so you're gonna be able to do it. Okay, all right. So I'm gonna take you back to the book now. Let's go to page 530 and let's go to how about 52? Okay, so we're gonna integrate. Now we have definite integral. So now we're gonna combine integration by parts with the fundamental theorem of calculus to actually evaluate definite integrals using integration by parts. So we're gonna have to integrate between 0 and pi over 8 x sec squared of 2x dx. Okay, so that's on page 530. And that's number 52. So as I mentioned, this is a combination of integration by parts and the fundamental theorem of calculus. So we have the definite integral from 0 to pi over 8 x sec squared 2x dx. Okay, so what's the class of x? It's the a, right? And this guy is the t, trig. This is trig and this is algebraic. Which one comes first in the I late? It's the a. So we're gonna choose v to be the x and the u prime to be secant squared 2x, right? This would be our choices of a u prime and v, right? So we're gonna introduce those choices. As such, what we get? What's the primitive of secant square 2x dx? So how about we do it on the side? What's the primitive of secant squared? Let's start with u du, where u is a function of x here. U is a function of x. Well, we know from Calc 1 that this is tangent u, right? And let's ignore the constant. Let's take the constant to be 0. Correct? If you differentiate tangent u with respect to x, you're going to get u prime secant squared, right? Okay. So you get this. And now back to this. We would like to integrate. So we would like to integrate secant squared 2x dx. Agree with me? Because you want to find u. You want to integrate this guy. Okay? Well, we're going to do a u substitution. Let's call it t substitution because the u is reserved for this guy. So let's call it t substitution. How about we use this as the t? How about we call it t instead? Okay. So let's call this t. If t is 2x, so if t is 2x, then dt is 2dx, correct? So dt is going to be 2dx, which means dx is going to be half dt. Agree with this? So one more time. If this is the t, if that's the t, question is what's dx? Well, dt then is 2dx, which means dx is half dt. Okay? So now we're going to use the u substitution here to obtain that this is equal to primitive secant squared t dx, but dx is half dt, so half dt. This is simple u substitution. And then now you employ this formula, you get half. So now you employ this formula right there, right? Because I have now the format and primitive secant squared t dt. This is half tangent t, and let's ignore the constant. Let's take the constant to be 0. That's what I mean. Okay. So all this guy is what's going on to transition from this side to this side. So I'm gonna write now u to be this entity, half t, half tangent t. Tangent t. And how much was t? 2x, right? 2x. So for completion, this is equal to half tangent 2x. Correct? Alright, so let me just take all of this, shrink it, and just place it right above this so you know what I'm talking about here, right? Where should I put it? Something like this. How about this here? Okay. So what's going on here is actually this package. Okay. Very good. And this is easy. So v prime is 1, right? Differentiate v, you get 1. Okay. So now all this package is going to be needed to transition from this to the new one. We're integrating by parts. So we get uv, so half x tangent to x, half x tangent to x, right? This is the uv part. And since it's definite integral, this is going to be evaluated between 0 and pi over 8. Okay. Minus the primitive, sorry, I'm gonna write it in an inclined fashion because I don't have room here. So between 0 and pi over 8, because this is a definite integral. And now we're gonna integrate u times v prime. And u is half tangent to x and v prime is 1. So you're gonna have the constant, multiplicative constant, half outside, tangent of 2x dx times the 1. So it's like this, right? Okay. Alright. So this is equal then to, let's do the evaluation. So half x now at the upper bound is going to be pi over 8 times tangent of 2 times x at the upper bound, so 2 times pi over 8, so pi over 4, right? Minus, at the lower bound, we evaluate this, it's going to be 0 times tangent of 0. Tangent of 0 is 0, so 0 times 0 is 0. You get this. Minus half times the definite integral between 0 pi over 8 tangent 2x dx. Alright, so now it comes down to integrating tangent of u du, or tangent of w dw. So let's recall this. From Calc 1. What's the primitive of tangent of w? W here is a function of x, right? Which is differentiable. Dw. What was this? This was minus ln of absolute value of cosine of w, right? Plus a constant. So recall this thing. And now let's employ it. So this is then equal to 1/2 pi over 8. Tangent of pi over 4, that's 1. That's 1. So pi over 8 then. So half pi over 8 minus half definite integral from 0 to pi over 8 tangent of 2x dx. So we're going to do u substitution here. So we're going to do w substitution, if you will. and then we're gonna adjust the bounds, correct? So let's do it on the side. Let's just do it on the side. So I want to find the definite integral from 0 to pi over 8 tangent of 2x dx. So apparently the w is gonna be the 2x, right? So the w is gonna be the 2x. If you take w to be the 2x, then dw is gonna be 2 dx, which means dx is half dw. Okay, I'm doing u substitution again. Let's call it w substitution here. And this is equal to the definite integral. We have to determine the bounds. Tangent of w dx. Dx is half dw, so half dw. And then the bounds, right? And then the bounds. The lower bound goes to the lower bound. So when x is 0, w is going to be twice 0, so 0. And when x is at the upper bound, pi over 8, w is going to be twice pi over 8, which is pi over 4, right? Okay. And that's equal to, now this is where this recall part is kicking in, right? It's right there. What are we going to get? We're going to get that this is equal to half times minus ln of absolute value of cosine w. So half times negative 1 is going to be negative half ln of cosine w, and w was taken between 0 and pi over 4, right? Okay. Alright. And this is equal to what? This is equal to negative half times ln of cosine w. Now at the upper bound is going to be cosine of pi over 4. That's positive. We don't need the absolute value. Anyway, let's just keep it. Minus ln of cosine of 0, because now at the lower bound we get this. Okay. Alright, and this is minus half times ln cosine of pi over 4 is square root of 2 over 2. Right? So square root of 2 over 2. Minus ln of cosine 0. What's cosine 0? Cosine 0 is 1, right? Cosine 0 is 1. So we obtain that this is actually ln of 1. And what's ln of 1? ln of 1 is 0. ln of 1 is 0. So long story short, this integral here is equal to minus half ln of square root of 2 over 2. Okay. Alright. You're gonna tell me, oh, should we simplify this writing and so on? Let's just keep it as is. Okay, so let's just keep it as is. If you would like to simplify it, feel free to do so, but this is as good as any other answer. So all this discussion was for this piece, right? Now we know exactly how much this piece is. It's exactly this number. So times what we found below, which was negative half ln of square root of 2 over 2. Okay. So all this discussion here, let's call it star. That's the star discussion that I can add right there. Because of this package, star package, I was able to replace this integral, this definite integral, by this value. Correct? Alright. And this is good enough. But let's simplify it. Why not? So pi over 16 here. Minus the minus is plus 1/4. 1/2 times 1/2 is 1/4. ln of square root of 2 over 2. Correct? So this would be the value of this definite integral that was given in number 52. Okay? So the last thing in this section is I want you to show the reduction formula that goes like this. The primitive of sine to power nx dx, and n is supposed to be an integer that's at least 2, is equal to this expression plus n minus 1 divided by n integral sine n to power sine to power n minus 2x dx. So here you're doing a reduction. You are instead of integrating sine to power n, you are down to primitive of sine to power n minus 2. So you reduce the power by 2, right? You chipped away 2 units from that power n. And n here is supposed to be at least 2, where n is an integer, right? This is useful because what you can do is you can eventually write the primitive of sine to power nx in terms of either you can do repeated application of this formula, and whatever this number n is, as long as it's 2 or more integer, let's say it's odd, eventually you can bring it down to primitive of sine to power 1x, right, by doing repeated application. And if n is an even number, even integer, that's at least 2, you're gonna bring it down to primitive of sine to power 0, which means primitive of 1 dx, right? In both cases, whether n is even or odd, you're gonna bring it down to a level where you know exactly what the primitive of that guy is. One time it's gonna be sine to power 1 x, so sine x, you know the primitive of sine x, and the other time is gonna be when n is even, you're gonna go down to primitive of 1 dx, and you know how to take the primitive of 1 dx. Okay. All right. So this reduction formula is useful, but obviously we need to prove it first, and hence the exercise. All right. So this completes this section.